Hello students, today we are going to cover Bohr model. Okay, so you can see my screen. So the pretext of Bohr model we should understand is that the nucleus has been discovered. Okay, so Bohr's atomic model, it is based on Rutherford's experiment, which is the alpha particle scattering experiment. So Rutherford found out about the nucleus which exists inside an atom. Further, Planck's quantum theory showed that the energy transferred through light or electromagnetic radiation, that energy has to be quantized. That means it has to be an integer multiple of h nu, where h nu is the energy of one photon. Okay, and Planck's quantum theory also was able to explain the observations of photoelectric effect. Okay, and the third thing was the line spectrum of hydrogen, which Bohr based in his atomic model on. Okay, so he observed that when hydrogen atoms uh, they undergo any absorption or emission of electromagnetic radiation, then uh, those photons, the photons are of specific wavelengths only. Okay, so this led to Bohr's formulation that the electrons must exist in some orbits called stationary orbits. Okay, and in these stationary orbits, when the electron is revolving inside a particular orbit around the nucleus it is revolving, it will not lose any energy. The energy will be constant. Okay, so the electron will have constant energy when it is in a particular orbit. Okay, it can be in various different orbits, but when it is in a particular orbit, then the energy will be constant. It will not lose any electromagnetic radiation energy. Uh, so basically, it is not following Maxwell's laws of electromagnetic radiation, which we had seen that Rutherford was not able to explain why the energy is not lost by electrons which are in the orbit, because they are accelerated particles. Electrons are undergoing circular motion, so it is accelerated motion in the under the influence of the electric field of the nucleus. So electrons, according to classical theory of electromagnetic radiation, they should lose some energy, and ultimately the electrons should follow this spiral path. They should, move closer and closer to the nucleus and ultimately merge with the nucleus. Okay, but that does not happen. So we can see that. Okay, so I'm going to dictate the points. You'll get the transcript. Okay, so for the postulates of Bohr model, let me dictate. So first of all, atoms contain a positively charged nucleus. All the protons and all the neutrons of the atom exist inside this particular nucleus, which is in the center of the atom. Okay, and electron. Um, I'm saying electron because there is only a single electron in the Bohr model. Okay, Bohr model is based on hydrogen atom only for hydrogen and hydrogen-like species which contain only a single electron. The Bohr model cannot be described for any other species which contain more than one electron. Okay. So there is a single electron, but it can be in any orbit, first orbit, second orbit, third orbit, and so on. And whenever it is in a particular orbit, it will be stable. Okay, it will not lose any energy in the form of electromagnetic radiation. Each orbit or each stationary orbit, it has a fixed energy level, and it is termed as a stationary orbit. Stationary, why? Because the energy is constant. Energy is not varying. Okay, that's why it is called a stationary orbit. It will not radiate energy as long as it continues to revolve in a particular orbit. Okay. Next thing is that the energy of these orbits will be different. Okay. The energy which is of the first orbit will be minimum. And as we move to higher orbits, the total energy of the electron will keep on increasing. And when we move infinitely far away from the nucleus, if we move far away, then infinitely far away, the energy will be maximum and it will become zero. Okay. So energy in any particular orbit will be less than zero. It will be negative. Okay. And the maximum amount of energy that an electron can have will be when it moves infinitely far away from the nucleus. Okay. When it moves infinitely far away, then its energy will become zero. Okay. That is the maximum amount of energy that an electron can have. So in the orbits, the energy will be negative. It will be less than zero. Okay. And energy level of any two different orbits must be different. And lower orbit will have less amount of energy, higher orbit will have more amount of energy. So these orbits, they are represented by a number. Okay, so orbit number 1, 2, 3, 4, and so on. We can name these, we can number these orbits, and these are, named as, uh, this will be K shell, this will be L, this will be M, this will be N. So K, L, M, N, O, P. Alphabetically, we can name these orbits, and we have to ensure that we use capital letters here. K, L, M, N, all are capital letters. Okay. So use capital alphabet to represent the shells or orbits. So shells here has a different meaning as compared to the shells that we see in quantum mechanical model. Okay, shell here is simply the path of electron or the stationary orbit in which the electron is revolving around the nucleus. Okay, shell has a different meaning in quantum mechanical model. When we say quantum numbers and we say the shells in which the electron is existing, that shell is different. Okay, here the meaning of shell is just the physical path or the trajectory of the electron when it is traveling in a particular orbit. Okay, so we can represent these shells in the form of a energy level diagram. Let me draw this diagram. We've seen this energy level diagram in atomic spectrum as well, right? So the lowest state or the first orbit n is equal to 1 will be called the ground state. Okay? And the higher orbits will be called excited states. Okay? N is equal to 2, n is equal to 3, n is equal to 4, and so on. All these are excited states. Okay? So the values of n can be anything. Okay? Finally, there will be uh, n is equal to infinity, which represents, an electron has moved infinitely far away from the nucleus. N is equal to infinity. So there are infinitely many shells in between the ground state and the infinity shell. Okay. So n is equal to 2 will be called the first excited state. N is equal to 3 will be second excited state. N is equal to 4 will be third excited state, and so on. Okay. So we have to ensure that we understand what an excited state means. An excited state is any state which is not the ground state. Okay. Ground state will be n is equal to 1, and any subsequent state n is equal to 2, 3, 4, and onwards, they will be excited states. So n equals to 2 will be the first excited state, the first level above ground state. Okay. So we have to understand these names. Okay. Now, next important thing is the quantization of angular momentum of an electron. So the next postulate is that the angular momentum of an electron in a particular stationary state is quantized. So the value of angular momentum L will be equal to mvr. This is the formula of angular momentum, and this must be an integer multiple of h upon 2 pi. This h upon 2 pi we can also write as h bar. We can write nh bar. Okay. So for angular momentum, you can write that the electrons revolve only in those orbits where the angular momentum of the electron is quantized. The angular momentum of an electron must be an integral multiple of h upon 2 pi. That's why only certain specific orbits are allowed. Angular momentum cannot be anything. Okay. Suppose I give you an example. What can be the value of angular momentum? That is equal to h upon 2 pi. Can this value exist? That is equal to h upon 3 pi. Can this value exist? H upon pi. Which values are possible? H upon 2 pi is, can it be expressed in terms of n h by 2 pi? Yes. N is equal to 1 will satisfy this condition. H upon 3 pi. Can this be n times h upon 2 pi? No, this is not possible. Can it be h upon pi? Yes, h upon pi can be written as 2 times h upon 2 pi, right? So it is an integer times h upon 2 pi. So this will be correct. Okay, there's nothing wrong with this. So the values of angular momentum cannot be any random values that you can think. Okay, they have to be an integer multiple of h upon 2 pi. Okay, so this is a very important point, which is to be understood in Bohr model. MBR is nh upon 2 pi. Next, postulate is that for an electron to maintain its stationary orbit, the centrifugal force felt by the electron should be balanced by the electrostatic force of attraction between the electron and the nucleus. Okay, so electron is basically traveling in a particular orbit. Okay, and it is feeling some attractive force towards the nucleus, and due to the circular motion, it will feel the centrifugal force. We call it this Fc, and this is uh, electrostatic force of attraction by the nucleus. We call it E. So this centrifugal force of attraction, the centrifugal force due to the circular motion should be balanced by this electrostatic force of attraction. Only then the electron will stay in the orbit, else it will move outward or inward. Okay, we don't want the electron to move outward or inward. We want it to stay in the circular orbit. So these two forces must be balanced at each and every point on this uh, orbit. Okay, so at each and every point, the centrifugal force will be balanced by the electrostatic force of attraction. Okay. Next postulate is that the energy of electron, it can be changed. Like if you want the electron to move to a higher orbit, the electron must absorb energy. Okay, so suppose I'm drawing two or subsequent orbits. If the electron wants to move from lower orbit n1 to higher orbit n2, then it needs to gain this amount of energy. If it wants to go from lower orbit to higher orbit, then it must absorb some energy. Okay? I'm writing the photon energy as h nu. Okay, so this particular electron will have to gain this h nu to move to higher orbit. And what happens when we want the electron to move from higher orbit to lower orbit? Suppose it wants to go from higher orbit to lower orbit, then it needs to emit this kind of the same amount of energy. Okay, so in this case, when the electron is moving from higher orbit to lower orbit, there is a decrease in energy, and that amount of energy will be released in the form of a photon. And when the electron wants to go from lower orbit or a lower energy level to a higher energy level, then it will need to absorb this amount of energy, which is the energy difference between the two orbits. Okay, so this also gives us the Bohr's frequency condition. Okay, So Bohr's frequency condition will be something like this. Change in energy, which is energy of higher orbit En2 minus energy of lower orbit En1. This must be equal to the energy of photon absorbed or emitted. If the electron is moving from N2 to N1, this much energy will be released. And if the electron is moving from N1 to N2, then this much energy will be absorbed. Okay. So whether absorption or emission is taking place, uh, that will be decided whether the electron is moving from lower orbit to higher orbit or from higher orbit to lower orbit. Okay. But the amount of energy will not change. Like, the energy difference between these two orbits is a fixed energy difference. Okay. That's why if the electron wants to move from lower orbit to higher orbit or from higher orbit to lower orbit, the same amount of energy will be absorbed in this case, and it will the same amount of energy will be emitted in this case. Okay. The energy of photon in both cases must be equal. This is the Bohr frequency condition. Okay. So if you state the point, uh, the frequency of radiation absorbed or emitted when transition occurs between two stationary orbits that differ in an energy of delta E, this much energy difference, will be En2 minus En1, and that will be equal to the energy of photon. It can be written as h nu or hc by lambda, depending on what is given to us in the question. Okay. Okay. So energy of photon, which an electron can accept or emit, this energy must also be quantized. The energy, like if you give, suppose this electron is there in this particular orbit, and I give this only this much amount of energy, will it be able to move from lower orbit to higher orbit? No. If the electron wants to move from higher orbit to lower orbit, it cannot release like more amount of energy. It has to release exact amount of energy, which is the energy difference between these two orbits. Okay. Even if I give more energy to the electron, this energy will also be not accepted by the electron. Okay. It has to be exactly the difference between the two energy levels. Okay. All right. Now the next thing is how to calculate the radius of a particular stationary orbit. Okay. Radius of nth orbit of any hydrogenic species will be n square divided by z times a naught, where this a naught is called the Bohr radius. And the value of a naught is equal to 0.529 angstroms. Okay. You have to remember this formula, how to calculate the radius of nth orbit. And sometimes question may be asked like, what is the radius ratio of two different orbits? Okay, this Z is atomic number of the hydrogenic species. So if hydrogen is there, Z is equal to 1. So Rn will be simply n square times a naught, right? But if some other hydrogenic species is given, suppose helium plus is given or lithium 2 plus is given, and for helium we have to understand that the atomic number will be 2. For lithium, the atomic number will be 3. Okay. For hydrogen, we have to take atomic number as 1. Okay. All right. So let's see an example. Okay. So the question is asking you to calculate the radius ratio of second Bohr orbit of lithium 2 plus and third Bohr orbit of helium plus. So this first one, let me call it R1. And what it is? It is second Bohr orbit of lithium 2 plus. Okay, so for R1, n is equal to 2. It is the second orbit. And Z, what is Z? For lithium 2 plus, that is equal to 3. Okay, and for the second orbit, we can see that the orbit number is 3. It is the third Bohr orbit, and the atomic number is what? Is 2. So for, we can write the radius formula for both. So the first one will be what? Will be n square by z. The formula is n square by z times a naught, right? So it will be 2 square by 3 into a naught. And for R2, what will be this? R2 will be equal to 3 square by 2 times a naught. Okay. Now, what will be the radius ratio? It will be R1 is to R2. It will be 2 square upon 3 a naught divided by 3 square upon 2 a naught. How much is it? Just 8 upon 27. Right? So these types of questions you can answer. Now, the next thing is speed of electron in the nth orbit. So speed in nth orbit will be z by n times v naught, okay, where v naught, the value is approximately 2.2 into 10 to the power 6 meters per second. We have to remember these constants. Okay, a naught Bohr radius is 0.529 angstrom. Sometimes we may be asked to calculate this. V naught is 2.2 into 10 to the power 6 meters per second. Okay. Example. We ask you to calculate speed of electron in fourth orbit of helium plus. Can I do it? Fourth orbit. So let me write it B4. This is what? Z by n times V naught. What is Z for helium plus? Z is equal to 2. It will be 2 divided by fourth orbit. So n is equal to 4, right? Times 2.2 into 10 to the power 6. How much is it? This is 1 upon 2. 1 upon 2 times 2.2 is 1.1 into 10 to the power 6 meters per second. Okay. So these kinds of questions we may be asked. Next thing is to determine the energy of the electron. Okay. So energy of nth orbit, this will be minus z square by n square into 13.6. Yeah, 13.6. So will be equal to minus 13.6 z square by n square electron volt per atom. So Z is atomic number, N is the orbit number, and 13.6 electron volts is the energy of the first orbit of hydrogen. Okay. So this energy levels also we must remember to some for some of the orbits we may be asked to calculate the energy. Okay. So the first 5 orbits I'm listing energy of first orbit. For hydrogen atom, energy of first orbit is minus 13.6 electron volts. Okay. Energy of the second orbit will be what? It will be minus 13.6 into, for hydrogen, z is equal to 1. So 1 square divided by 2 square. So 13.6 divided by 2 square, or that is 13.6 divided by 4, that will be minus 3.4 electron volts. Energy of third orbit will be minus 13.6 into 1 square divided by 3 square. So minus 13.6 divided by 9 will be minus 1.51 electron volts. Energy of fourth orbit will be how much? It will be minus 13.6 divided by 4 square minus 0.85 electron volts. And lastly, energy of the fifth orbit, this will be minus 13.6 divided by 5 square. Okay, it will be minus 0.54 electron volts. So you have to remember these values. Okay, sometimes it may be useful. Now, if I ask you how much energy will be required for the electron to move from second orbit to the fifth orbit, can you calculate that? We had seen the Bohr frequency condition. What is the Bohr frequency condition? That the energy difference should be the energy of photon absorbed. Okay, so here the electron is going from a lower orbit to a higher orbit. That's why you can say the energy required, delta E, or energy of photon, this must be equal to energy of higher orbit, En2, which is E5, minus energy of lower orbit, E2. Okay, what is E5 minus E2? Energy of fifth orbit is minus 0.54, minus energy of second orbit is how much? Minus 3.4 electron volts. How much it will be? 3.4 minus 0.54 will be right. Just a minute. Okay, so yeah, we were seeing how to calculate the energy difference between the fifth orbit and the second orbit. So fifth orbit energy is say, minus 0.54, and the energy of the second orbit is minus 3.4. Okay, how much will be this energy? It will be 2.86 electron volts. So this much energy will be required if the electron wants to move from the second orbit to the fifth orbit. Okay. All right. The next thing that we need to understand is the kinetic energy and potential energy of the electron. So we just need to remember this formula, that kinetic energy of the electron will be negative of the total energy, and this will be, so total energy, we know the formula, mass 13.6 z square by n square. So this will be what? It will be plus 13.6 times z square by n square. Okay. Electron volts per atom. This is the kinetic energy of electron. Now what will be the potential energy of electron? It will be twice of the total energy. Okay. What will be the potential energy? Total energy was minus 13.6, and 2 times that will be how much? It will be 27.2. Minus 27.2 times z square by n square. We don't need to remember these formulas. We just need to remember the relation between the total energy, potential energy, and kinetic energy. You can write the, you can just remember this formula, which I'm writing as like summary of all this is energy of electron. The total energy will be equal to negative of the kinetic energy, and it will be half of the potential energy. This is the only formula that you need to remember when you're asked to relate the total energy, kinetic energy, and potential energy of the electron. Okay. Alright. Next thing that you need to understand is how do you calculate the ionization energy, excitation energy, and binding energy of the electron. Okay. First one is excitation energy. So if the electron wants to move from the ground state to any excited state, this is the nth excited state. What will be the orbit number? It will be n plus 1, right? We had seen that the first excited state was n is equal to 2. Second excited state was n is equal to 3, right? So the nth excited state will be what? It will be n plus 1, right? You can see that this third excited state is n is equal to 4. So what will be the nth excited state? It will be n plus 1. Okay. So excitation energy, you need to understand what this energy means. It is the energy required to bring an electron from the ground state to nth excited state. Okay. So the energy required to promote or excite an electron from the ground state n is equal to 1 to any higher energy level in a hydrogenic atom. That amount of energy will be called the excitation energy of the electron. Okay. What will be first excitation energy? First excited state is n is equal to 2. So it will be E2 minus E1. So to excite an electron from the ground state to the first excited state, which is n is equal to 2, that will be first excitation energy. Okay. You can calculate this. Second term is called the binding energy. It's also called the separation energy. This binding energy or separation energy means what? It is the minimum energy required to eject or free or remove the electron from the nth quantum state of a hydrogen atom or any hydrogen species. So if the electron is in any particular excited state, the electron is right here, okay, and you want to remove the electron from the atom, you want to bring it to infinity, okay. So this amount of energy will be called the binding energy or the separation energy required for the electron to be removed from the atom. So binding energy of the nth quantum state will be uh, minus of En, okay, because the energy right here at infinity is zero, right? The energy of the nth quantum state will be what? Energy of n. So what will be the energy required to bring the electron from this energy level to n is equal to zero? It will be 0 minus of En. So binding energy can be written as minus of En. Okay. And separation energy also has a similar definition, but if you require that separation energy is defined with respect to the excited state. Okay. So nth separation energy will be what? It will be the energy required to remove the electron from nth excited state. Okay. All right. The third term will be the ionization energy. And as the name suggests, it is the energy required to remove an electron from the ground state. So an electron which is existing in the ground state, if you want to bring it to infinity, or if you want to remove the electron from the atom, that amount of energy, it will be called the ionization energy. Now, imagine for any state, if I want to, any stationary state, if I want to write the relation between ionization energy and binding energy and excitation energy, what can be that relation written as? You see, this is n is equal to infinity level. This is any nth quantum state, and this is the ground state. And this is okay. So this much energy will be required to excite the electron from the ground state to the nth quantum state, and this much energy will be required to remove an electron from the nth excited state. Uh, from the excited state, this is the binding energy or the separation energy. This is the excitation energy, right? And this will be the amount of energy that will be required to remove an electron from the atom altogether from the ground state. Okay. So are you able to identify the relation between these three energy terms? You can say ionization energy is the sum of excitation energy and binding energy. Okay. Now let's see an example of how to calculate the ionization energy and the binding energy. The ionization energy can be written as energy of infinity minus energy of the first quantum state. It can be written as minus of E1, right? 0 minus E1 will be minus of E1. You can remember this formula. Okay. So what is the ionization energy of hydrogen atom? Ionization energy can be written as minus of E1. And what is minus of E1? It is a minus of minus 13.6 times Z square by N square, right? This is the formula for energy. And what is Z for hydrogen? Hydrogen is atomic number 1. So Z is equal to 1 square divided by N square. And what is N? For the first quantum state, N is equal to 1. So 1 square divided by 1 square will be 1. And minus of minus 13.6 will be plus 13.6. So the initial energy of hydrogen will be 13.6 electron volts per atom. So N is one. So N is one hydrogen atom. For bringing out the electron from the ground state of the hydrogen atom, we need to provide it 13.6 electron volts amount of energy. Okay. Now the second state, the second question was ionization energy of helium plus. What will be the ionization energy of helium plus? It will be minus of E1 for helium plus. Okay. So what will be this? Minus of minus 13.6 times Z square upon N square. What is Z? For helium plus, Z is equal to 2. So 2 square divided by E1. So N is equal to 1. This is the first orbit we are talking about, 1 square. So it will be 2 square. 4 times 13.6. Minus minus will be plus. So 13.6 into 4 will be how much? 52 plus 2.4, 54.4 electron volts per atom. Okay. All right. So these kinds of questions you can answer based on the formulas of excitation energy, binding energy, and annihilation energy. We can calculate these when required. Okay. Now, next thing is we're going to talk about the drawbacks of Bohr's atomic model. So, first drawback is that Bohr's atomic model is based on like it gives the atomic description only for hydrogenic species only. Okay. Only hydrogenic species are there. The normal other atoms, they cannot be described by Bohr model, which contain more than one electron. They cannot be uh, you know described by the Bohr model. Bohr model is applicable only for hydrogen atom and hydrogenic species, which contain only a single electron. There are very few atoms or ions which will fit that category. If you want a general atomic model, Bohr's model is not sufficient. Okay. Second drawback was that Bohr was not able to explain why the stationary orbits are stable. He just assumed that the angular momentum will be quantized and that will make the orbit stable. But why is that the case? That was not being able to be satisfactorily answered by Bohr. Okay. The next thing that we can see, the third drawback is that Bohr ignored the wave nature of electron. Okay. Subsequently, in later experiments, it was found out that matter also has some wave characteristics, particularly electrons inside atoms. They will have some wave characteristics due to which they will not directly, follow the laws of motion of which are applied to us basically. Okay. Since they have some wave characteristics, we have to consider those characteristics also when we try to describe the atom. Okay. So that was the drawback of Bohr. Okay. All right. So today we have covered the Bohr model in brief, and the major things that you need to understand is how to apply these formulas, which is if you want to calculate some radius or speed of the electron or energy of electron, kinetic energy, potential energy, and these terms. So majorly questions which are asked are based on these formulas only. Okay. So make sure that you have clarity in how to apply these formulas. Okay. All right. Thank you.